In 2018 and 2019, two aircraft crashed within 5 months. 346 people died. Boeing did not collapse as a company, but a system inside it failed. For decades, Boeing represented engineering discipline. Safety was embedded in culture. Redundancy was non-negotiable. Then incentives shifted. Speed became a competitive weapon. Certification processes accelerated. Software was used to compensate for hardware decisions. When the 737 MAX failed, the issue was not a single sensor. It was organizational drift, cost pressure, time to market urgency, delegated oversight. The crisis was not a technical anomaly. It was governance stress exposing structural misalignment between engineering and capital markets.
Boeing's identity was built on engineering discipline. Founded in 1916, it grew alongside modern aviation. Safety was embedded as a design principle. Redundancy was engineered into critical systems. Certification processes were historically rigorous. Engineering authority carried institutional weight. Aircraft programs were long-cycle undertakings. Testing phases were extensive. Design margins were conservative. Reputation depended on reliability. Commercial airlines selected Boeing for durability. Regulators trusted its internal controls. The 707 and 747 programs established global leadership. Wide-body aircraft became symbols of American aerospace scale. Engineering culture emphasized failure analysis. Lessons from past incidents shaped new standards. Design review boards held veto authority. Program managers were accountable to engineering leadership. Supplier networks were integrated through quality oversight. Manufacturing discipline supported certification integrity. The company operated within a regulated global framework. Federal Aviation Administration oversight was embedded in process. Documentation standards were extensive. Compliance audits were routine. Engineering decisions were historically prioritized over schedule. Commercial performance followed technical credibility. Margins were built on reliability rather than speed. Institutional memory reinforced caution. Risk assessment was procedural. Flight control systems were layered with safeguards. Hardware solutions were preferred over software intervention. Certification cycles aligned with regulatory consultation. Investor expectations were secondary to aircraft integrity. For decades, this model produced durable outcomes. Airlines ordered aircraft years in advance. Backlogs provided visibility. Capital expenditure was planned long-term. Engineering leadership influenced executive direction. However, the aerospace market evolved. Competition intensified. Airbus introduced fuel-efficient narrow-body aircraft. Airlines demanded operating cost reductions. Shareholder expectations increased. Return metrics became more prominent. Program timelines faced compression pressure. Production rates accelerated. The balance between engineering margin and commercial urgency shifted. Cultural priorities adjusted incrementally. The organization remained outwardly stable, but incentives began to realign internally. Structural takeaway: a legacy of engineering discipline can erode gradually when commercial incentives shift beneath it.
By the early 2010s, the narrow-body aircraft market intensified. Airbus launched the A320neo with more fuel-efficient engines. Airlines responded quickly with strong orders. Fuel efficiency became a decisive purchasing factor. Operating cost per seat influenced fleet strategy. Boeing faced the risk of losing market share. A new aircraft program would require significant capital. Development timelines would extend several years. Regulatory certification would reset. Instead, leadership evaluated modification of the existing 737 platform. The 737 had decades of operational history. Airlines were familiar with its cockpit configuration. Pilot training transition costs were lower. Maintaining common type rating was commercially attractive. A derivative model appeared faster to market. Time became a strategic variable. Order books required reassurance. Production continuity depended on competitive positioning. Engineering teams assessed engine placement constraints. The new engines were larger in diameter. Airframe geometry imposed physical limitations. Ground clearance was restricted by landing gear height. Repositioning engines altered aerodynamic characteristics. Aircraft pitch behavior required evaluation. Software intervention emerged as a solution path. A hardware redesign would increase cost and delay. Software modification preserved schedule. Internal debate centered on feasibility. Certification classification influenced training requirements. Maintaining minimal pilot retraining preserved airline economics. Competitive urgency shaped decision sequencing. Capital markets monitored order flow closely. Executive compensation aligned with delivery performance. Program launch timing affected quarterly outlook. Engineering compromise remained within regulatory tolerance. Risk assessment models considered probability thresholds. Historical safety records supported confidence. Derivative classification simplified regulatory engagement. Delegated authority structures accelerated review cycles. Airbus continued accumulating orders. Market narrative emphasized efficiency. Boeing announced the 737 MAX program. Externally, the strategy appeared pragmatic. Internally, constraints were being absorbed. Aerodynamic adjustments required precise calibration. Software authority expanded within flight control logic. Schedule discipline tightened. Testing cycles were managed carefully. Regulatory coordination proceeded under delegated frameworks. Commercial momentum was restored temporarily. Structural takeaway. Competitive pressure can compress design timelines, shifting technical trade-offs toward speed rather than structural redesign.
With the 737 MAX program approved, design decisions accelerated. The objective was to preserve commonality with previous 737 variants. Airlines expected minimal pilot retraining. Simulator requirements were viewed as cost variables. Engineering teams evaluated structural redesign options. A clean sheet aircraft would reset certification classification. It would also extend development timelines significantly. Capital expenditure would increase materially. Instead, the derivative pathway was prioritized. Engine placement adjustments altered aerodynamic balance. The larger LEAP engines were mounted further forward and higher. This changed the aircraft's pitch characteristics at high angles of attack. Hardware design of landing gear was constrained by airframe legacy. Physical geometry limited structural modification. Software became the mechanism to compensate for aerodynamic shift. The Maneuvering Characteristics Augmentation System was introduced. MCAS was designed to adjust nose-down trim automatically. It activated under specific flight conditions. The system relied on angle of attack sensor input. Initial architecture referenced a single sensor source. Redundancy design choices were debated internally. Engineering assumptions focused on statistical failure likelihood. Risk probability models supported certification strategy. The derivative classification reduced regulatory friction. Pilot interface documentation described MCAS in limited detail. Training materials emphasized continuity with earlier models. Simulator requirements were minimized. Airline economics were preserved. Engineering review boards approved implementation. Testing scenarios validated expected performance envelopes. System authority thresholds were calibrated. Software activation was not prominently highlighted in marketing materials. Internally, documentation expanded. Externally, communication simplified. Time to market targets remained fixed. Delivery commitments influenced milestone pacing. Program management prioritized schedule adherence. Engineering teams balanced compliance with delivery pressure. Regulatory engagement occurred through delegated authorization structures. Technical risk remained within modeled assumptions. The aircraft entered production. Order backlog remained strong.
competitive narrative stabilized temporarily. However, design reliance on software intervention increased. Operational behavior now depended on algorithmic correction. Structural margin narrowed. The system functioned within design envelope, but sensitivity to sensor integrity became critical. Structural takeaway: choosing modification over redesign can transfer structural complexity from hardware into software dependencies.
MCAS was designed as a stability augmentation system. Its purpose was to adjust pitch automatically in specific conditions. The system activated during high angle of attack scenarios. It commanded nose-down stabilizer trim. The objective was to align handling characteristics with previous 737 variants. Certification classification depended on continuity. Maintaining common type rating reduced pilot retraining requirements. MCAS operated in the background. It was not presented as a primary flight control system. The logic relied on input from angle of attack sensors. In its initial configuration, activation referenced a single sensor. Redundancy architecture was limited at entry into service. Engineering risk assessments modeled low probability of sensor failure. Failure scenarios were evaluated within statistical thresholds. System authority allowed repeated trim inputs. Activation resets were linked to pilot counter-trim. Under normal operation, MCAS intervention was expected to be rare. The system was not prominently detailed in flight manuals. Pilot training materials emphasized aircraft similarity. Simulator sessions specific to MCAS were not mandated. Cost and schedule alignment remained priorities. Certification review proceeded through delegated authority frameworks. The Federal Aviation Administration relied in part on manufacturer analysis. Documentation described MCAS as augmentation rather than redesign. Internally, system authority discussions occurred among engineers. Concerns were documented regarding sensor dependency. Resolution decisions maintained schedule continuity. Program management evaluated trade-offs against delivery commitments. Airline customers prioritized minimal transition friction. Market communication highlighted fuel efficiency gains. Software complexity increased within flight control architecture. Hardware modification remained constrained by legacy geometry. Testing validated compliance within defined envelopes. Edge case stress conditions were limited in simulation. Operational data was expected to confirm assumptions post-delivery. The aircraft entered service in 2017. Initial deployments proceeded without major public attention. Production rates increased to meet backlog demand. Delivery cadence reinforced commercial momentum. Internally, system familiarity remained concentrated among specialists. Externally, the aircraft was presented as an incremental upgrade. Certification documentation satisfied regulatory thresholds. However, authority delegation blurred oversight boundaries. System reliance on a single sensor remained embedded. Pilot awareness of automatic trim behavior was incomplete. Incentive alignment favored continuity over disclosure expansion. Governance structures assumed statistical sufficiency. Redundancy was reduced relative to historical design culture. Software authority substituted for hardware margin. Organizational confidence remained intact. Market expectations stabilized. Risk models reflected acceptable tolerance. Structural dependencies were now embedded in code. The aircraft operated within design assumptions, but the margin for sensor integrity had narrowed. Structural takeaway: when software compensates for hardware constraints, governance must expand oversight proportionally, or structural dependency increases. Certification of the 737 MAX occurred within established regulatory frameworks. The Federal Aviation Administration operated under delegated authority structures. Organization Designation Authorization allowed manufacturer engineers to perform portions of compliance verification. This delegation was not unique to this program.
It had evolved over decades to manage regulatory workload. However, delegation requires clarity of responsibility. Internal engineers performed safety assessments. Hazard classifications influenced system redundancy requirements. MCAS was categorized within acceptable risk thresholds. Failure probability assumptions supported its design authority. Single sensor reliance was evaluated under those assumptions. Redundancy was not mandated under the assigned classification. Documentation flowed through structured review processes. Regulatory officials reviewed summarized analyses. Time to certification remained a program objective. Competitive timelines influenced pacing. Airline commitments depended on delivery windows. Internal resource allocation prioritized milestone adherence. Engineering sign-offs moved through layered management channels. Communication between technical specialists and oversight bodies compressed. Risk language was framed within probability metrics. Operational impact scenarios were modeled. Pilot workload assumptions informed classification decisions. Simulator requirements were evaluated against training cost. Maintaining common type rating remained commercially central. Certification documentation described MCAS as incremental. System authority details were not extensively emphasized in pilot materials. Delegated engineers balanced dual accountability. They represented both regulatory compliance and corporate objectives. Incentive structures rewarded program continuity. Production schedules aligned with certification milestones. The aircraft received approval for service entry. Acceleration deliveries. Airlines integrated the 737 MAX into fleets. Operational data began accumulating. Regulatory comfort reflected historical safety performance. Confidence in statistical modeling persisted. Internal dissent did not translate into structural pause. Oversight boundaries remained procedural rather than structural. Delegation efficiency reduced friction, but reduced friction also reduced independent scrutiny. The separation between regulator and manufacturer narrowed functionally. Certification culture emphasized compliance documentation. Less emphasis was placed on adversarial challenge. Governance frameworks assumed good faith alignment. Incentives remained commercially oriented. Engineering culture had shifted subtly from veto authority to integration. No single decision defined the outcome. Instead, incremental accommodations accumulated. Risk thresholds remained technically defensible, yet structural independence had weakened. Certification proceeded within rules, but rules were interpreted through organizational incentive filters. Structural takeaway. Delegated certification requires structural independence. When incentives align too closely, oversight shifts from adversarial review to procedural validation.
As the 737 MAX entered service, internal communication channels were tested. Engineering teams monitored operational feedback. Initial data did not trigger systemic alarm. However, internal messages reflected awareness of sensitivity concerns. Discussions occurred regarding simulator behavior. Pilot transition assumptions were revisited informally. Concerns about system authority surfaced in technical correspondence. These concerns were not elevated structurally. Organizational hierarchy filtered communication flow. Program management prioritized continuity. Delivery schedules remained intact. Airline onboarding continued. Internal debate remained compartmentalized. Documentation reflected compliance, not escalation. Risk assessments remained within statistical framing. The absence of prior incidents reinforced confidence. Specialists understood MCAS logic. Line pilots did not have full system visibility. Training materials maintained simplicity. Communication between engineering and flight operations narrowed. Corporate messaging emphasized product efficiency. Investor briefings focused on order strength.
Internal emails reflected tension between engineering caution and schedule discipline, yet no formal pause occurred. Escalation thresholds were procedural. Authority to suspend delivery required multi-level consensus. Incentive structures discouraged disruption. Production rates continued. Software documentation remained technical rather than operational. Cross-functional alignment meetings prioritized delivery metrics. Governance processes assumed existing safeguards were sufficient. The derivative classification constrained reconsideration. Redesign discussion was not reopened. Risk language remained probabilistic. Operational anomalies were viewed individually. Systemic interpretation lagged behind localized review. Delegated oversight mechanisms remained procedural. No structural alarm was triggered. Internal reporting channels operated within established boundaries. Engineering culture had evolved from veto authority to integration. Financial performance metrics remained central. Schedule adherence preserved market confidence. The organization remained outwardly stable. However, misalignment between information flow and authority became clearer internally. Technical knowledge concentration limited broader awareness. System documentation complexity reduced transparency. Software dependency increased operational sensitivity. The aircraft operated across global fleets. Operational environments varied. Data interpretation remained centralized. Escalation required threshold breach. Threshold definition was narrow. Governance assumed incremental correction. Incentives favored continuity. The structure did not fail visibly, but communication elasticity had weakened. Structural takeaway. When communication is filtered through schedule incentives, early warning signals can remain localized rather than structural.
On October 29, 2018, Lion Air Flight 610 departed Jakarta. The aircraft was a 737 MAX 8 delivered earlier that year. Shortly after takeoff, pilots reported control difficulties. Angle of attack sensor data fed erroneous input to flight systems. MCAS activated in response to the sensor reading. The system commanded nose-down trim. Pilots countered with manual input. MCAS reactivated after reset conditions were met. Repeated trim commands increased control pressure. Cockpit workload intensified. Airspeed and altitude data became inconsistent. The flight crew attempted stabilization procedures. Communication with air traffic control reflected uncertainty. The aircraft entered a descending trajectory. The flight impacted the Java Sea. All 189 people on board were lost. Initial investigation focused on sensor malfunction. Maintenance records were reviewed. Replacement of the angle of attack sensor occurred prior to flight. Investigators analyzed flight data recorder output. MCAS activation sequences were reconstructed. Repeated nose-down trim commands were confirmed. Pilot awareness of MCAS functionality was examined. Training materials were scrutinized. Certification documentation was revisited. Boeing issued an operations bulletin. Regulators initiated technical review. The aircraft remained in service globally. Deliveries continued. Internal assessment focused on software update development. MCAS logic modification was proposed. Dual sensor comparison was evaluated. System authority limits were reconsidered. However, the aircraft was not grounded immediately worldwide. Operational confidence remained partially intact. Risk interpretation remained incremental. The event was framed initially as maintenance and sensor failure. System design implications were debated. Airlines awaited formal regulatory direction. Production schedules continued. Investor communications emphasized corrective action. Software revision timelines were outlined. The organization entered a reactive phase. The incident exposed system dependency on sensor integrity.
It revealed pilot awareness gaps. Governance structures reassessed oversight boundaries, yet structural pause was not immediate. Global fleet operations persisted. The narrative remained technical rather than structural. Confidence erosion began. The organization prepared incremental correction. The first crash did not represent a random anomaly. It represented interaction between design dependency and operational reality. Structural takeaway. When system design concentrates authority in automated correction, a single-point failure can escalate into structural vulnerability.
On March 10, 2019, Ethiopian Airlines Flight 302 departed Addis Ababa. The aircraft was a 737 MAX 8 delivered months earlier. Shortly after takeoff, pilots reported flight control instability. Flight data indicated repeated nose-down trim inputs. Angle of attack sensor discrepancies were recorded. MCAS activation patterns resembled the prior Lion Air sequence. Pilots attempted standard recovery procedures. Manual trim inputs were applied. Automatic trim commands resumed. Cockpit workload increased rapidly. Airspeed and altitude indicators conflicted. The aircraft entered a steep descent. The flight impacted terrain minutes after departure. All 157 people on board were lost. Global aviation authorities responded swiftly. Regulators began reviewing similarities between incidents. Flight data comparisons confirmed common activation behavior. Software authority and sensor dependency became central issues. Within days, countries began grounding the 737 MAX. On March 13, 2019, U.S. regulators ordered grounding. Deliveries halted. Production schedules were reassessed. Airlines removed the aircraft from service. Market confidence deteriorated sharply. Equity valuation declined. Investor scrutiny intensified. Congressional inquiries were announced. Regulatory hearings were scheduled. Delegated certification practices were questioned publicly. Internal communications were subpoenaed. Software modification timelines accelerated. Dual sensor validation logic was implemented. MCAS activation authority was limited. Pilot training requirements were expanded. Simulator sessions became mandatory. Documentation transparency increased. The narrative shifted from anomaly to systemic review. Governance culture entered examination. Engineering oversight processes were scrutinized. Delegated authority frameworks were reassessed. Production inventory accumulated. Cash flow pressure increased. Supplier networks experienced disruption. Reputational impact extended beyond a single program. Airline compensation negotiations began. Financial losses accumulated. The second crash removed ambiguity. Systemic interpretation replaced incremental framing. The organization faced simultaneous technical and governance challenge. Structural misalignment became visible externally. Incentive structures were questioned. Engineering authority was reevaluated. The grounding marked a structural inflection point. Confidence required demonstrable reform. Structural takeaway. Repeated failure under similar conditions converts technical explanation into governance examination. Following the global grounding in March 2019, deliveries halted immediately. Airlines suspended 737 MAX operations worldwide. Undelivered aircraft accumulated in storage facilities. Production rates were reduced gradually. Cash flow dynamics shifted rapidly. Customer compensation negotiations began. Airlines sought financial relief for grounded fleets. Balance sheet pressure increased. Inventory carrying costs expanded. Supplier contracts required renegotiation. Workforce planning entered uncertainty. Capital markets reacted to sustained grounding. Equity valuation declined materially. Credit outlook faced scrutiny.
Analysts revised earnings forecasts downward. The company announced estimated financial impact in the billions. Quarterly losses reflected halted deliveries. Free cash flow turned negative. Debt issuance increased to preserve liquidity. Investor confidence required regulatory clearance. Certification, recertification became central objective. Software revisions were finalized. Dual sensor comparison logic was incorporated. MCAS activation authority was limited. Pilot training requirements expanded. Simulator sessions became mandatory for MAX crews. Regulatory review extended beyond software. System architecture was reassessed. Documentation transparency increased. Global aviation authorities coordinated evaluation. Test flights were conducted under observation. Public hearings examined decision-making processes. Congressional committees questioned certification delegation. Internal communications were disclosed publicly. Governance practices faced external evaluation. Leadership changes followed executive accountability review. Board oversight structures were adjusted. Risk management frameworks were updated. Production of the 737 MAX was temporarily suspended. Inventory management became logistical challenge. Supplier stability required coordination. Airline relationships required rebuilding. Re-entry into service required phased approval. Confidence restoration depended on demonstrable reform. The crisis extended beyond engineering. It affected capital allocation priorities. Debt levels increased to manage liquidity. Share repurchase programs were halted. Dividend policy was reconsidered. Strategic focus narrowed to stabilization. Operational discipline replaced growth ambition. The grounding period became structural inflection. Financial impact accumulated alongside reputational cost. Governance reform became prerequisite for recovery. Structural takeaway. When operational grounding halts revenue, financial resilience depends on governance credibility as much as liquidity.
After the grounding governance review expanded beyond technical correction, board oversight processes were evaluated. Executive incentive structures were examined. Compensation metrics were reassessed. Safety reporting channels were reviewed. Engineering authority lines were clarified. The relationship between management and technical leadership was scrutinized. Cultural assessment initiatives were launched. External advisors were engaged. Regulatory communication protocols were revised. Certification delegation structures were reconsidered. Transparency policies were expanded. Internal audit functions were strengthened. Risk committees increased reporting frequency. Documentation practices were updated. Engineering escalation pathways were formalized. Software development oversight was tightened. Training standards were elevated. Pilot documentation was revised for clarity. Regulatory cooperation became more structured. International authorities participated in joint review processes. Public trust required demonstrable accountability. Leadership changes occurred at senior levels. Board composition evolved. Safety committees were reinforced. Internal messaging emphasized engineering primacy. Capital allocation decisions reflected conservative posture. Share repurchase programs remained paused. Debt reduction became secondary to stability. Operational readiness required regulatory validation. Airline confidence depended on independent review. Investor communication shifted tone. Earnings guidance became conservative. Delivery forecasts incorporated risk buffers. Program management adopted extended testing cycles. Safety metrics received higher board visibility. Cross-functional communication frameworks were strengthened. Documentation depth increased across programs. Engineering sign-off authority was reaffirmed. Regulatory engagement became less delegated and more direct.
Organizational learning initiatives were formalized. Crisis management protocols were updated. Incentive metrics integrated safety performance indicators. Governance realignment required structural reinforcement. Recovery planning balanced liquidity and credibility. Reputational repair required sustained transparency. Operational discipline replaced acceleration emphasis. The organization remained intact, but governance architecture had shifted. Engineering culture regained formal priority. Market performance stabilized gradually. The program returned to service under scrutiny. Structural takeaway. Governance reform after crisis requires aligning incentive structures with engineering authority to restore institutional credibility.
The 737 MAX crisis did not dissolve the company, it exposed structural tension within it. For decades, engineering authority defined program decisions. Safety redundancy was institutional doctrine. Competitive dynamics altered that balance. Time to market became strategic variable. Derivative design replaced clean sheet redesign. Software compensated for hardware constraints. Certification delegation accelerated review cycles. Incentive structures favored delivery continuity. MCAS concentrated authority within automated correction. Single sensor dependency narrowed redundancy margin. Communication channels filtered early technical concern. Risk assessment relied on statistical probability. Delegated oversight reduced adversarial scrutiny. The first crash in October 2018 signaled system stress. The second crash in March 2019 removed ambiguity. Global grounding halted revenue flow. Financial exposure expanded rapidly. Governance became subject to public examination. Congressional hearings questioned delegation practices. Regulatory review extended internationally. Leadership changes followed structural scrutiny. Board oversight was reinforced. Incentive metrics were recalibrated. Safety reporting lines were strengthened. Software authority was limited. Pilot training standards increased. Transparency improved documentation depth. The organization remained operational. Manufacturing continued under revised oversight. Recovery required structural adjustment. Financial losses were measurable. Reputational impact was intangible. Engineering culture required reassertion. Competitive pressure did not disappear. Airbus continued market presence. Capital markets maintained expectations. Operational discipline required sustained reinforcement. Incentive alignment became central governance objective. The crisis did not originate from a single line of code. It emerged from cumulative accommodation. Incremental trade-offs compounded. Structural dependencies increased quietly. Software authority substituted for hardware margin. Oversight elasticity weakened gradually. No single decision defined failure. The system functioned within defined parameters, but parameters were shaped by incentives. When stress exceeded assumptions, vulnerability surfaced. Corporate collapse can occur inside a functioning enterprise. It need not involve bankruptcy. It can manifest as governance drift. Engineering integrity depends on structural alignment. Incentives shape outcomes. Corporate collapse can occur inside a functioning company when governance drifts from mission. Structural takeaway. Incentives shape outcomes, and corporate collapse can occur inside a functioning company when governance drifts from mission.